Hi guys, I hope you must be enjoying physics. If even if you are not enjoying, do study because it's important. Okay, so let's start with work power energy, objective 1 from HC Verma. And let's start with the first question. A very heavy stone is thrown from a cliff of height h with the speed v. The stone hit the ground with maximum speed if it is thrown. The speed doesn't depend on the initial direction because the loss in potential energy will be same, so they will be same in gain in kinetic energy. And in all the cases, whether you throw it horizontally downward or vertically upward, if you are throwing with the same speed, then the final speed will also be same. In the next question, there are two springs A and B which are stressed by applying same force or same magnitude force on their ends. If the energy stored in A is E, then the energy stored in B. Obviously, the spring constant of B is less than spring constant of A. So stretch in the string B, stretch in the spring B will be more than spring A. Let's look at the diagram. This is 2K and this is K. It is B, it is A. Let the elongation in A is x naught. So we can say the force will be 2x naught, which is F. So the same force, 2x naught force, will give you y naught elongation in B. So that y naught is nothing but 2x naught. So the elongation in B is double that of A because the spring constant is half that of A. Okay. So if potential energy of A, which is half its spring constant 2K into elongation square, is E, then the potential energy in B will be half its spring constant 2x, which is the elongation in B whole square. You will get as 2e. This value, if this value is E, this value will be 2e. Okay. Two equal masses are attached to two ends of a spring of spring constant K. Masses are pulled out symmetrically to stretch the spring by a length x over its natural length. The work done by spring on each of the mass. The total work done by the spring will be minus half kx square. Negative sign indicate that the displacement of the point or the masses will be opposite to the force applied by the spring. So total work done by the spring will be minus half kx square. As there are two masses, so on each mass the work done will be minus 1 by 4 kx square. This is the logical solution which I gave you. We can prove that mathematically also. So let's say at a moment the elongation is y and we displace it further by dy by 2 and dy by 2, so the elongation is increased by dy. Okay, hence the work done on this mass, because at this moment force by the spring will be ky, it will be ky, and the displacement of this block will be dy by 2 cos of 180 because they are opposite. So we get, when we integrate y from 0 to x, when we integrate y from 0 to x, we'll get half kx square, because the variable is y and it is moving, it is changing from 0 to x. X is the final elongation. So the work done by the spring on a single block will be minus half kx square. Next is the negative of the work done by the conservative internal forces on the system is equal to, we can say, negative of the work done by conservative forces. They need not to be internal. So the work done by conservative forces with a negative sign is nothing but change in potential energy. Uh, Basically, it is the definition of potential energy. So negative of the work done by conservative forces is delta U, or change in potential energy. Next is the work done by the external force on a system equals to, in my opinion, the answer should be D, but the answer is given as uh, A. Okay, so answer can be A only when we assume that the total energy is mechanical energy and there is no work done by internal non-conservative forces. Under these two assumptions, answer can be A. Okay, first is that we mean total energy as mechanical energy, and no work is done by internal non-conservative forces, because there can be some internal non-conservative forces which will be doing work. So if we assume that no work is done by them, then answer will be A. I think uh, this book has assumed that, which in my opinion is not very accurate assumptions, and in my opinion answer should be D. Sixth is work done by all the forces, external and internal. It consists conservative as well as non-conservative also. On a system is equal to change in kinetic energy of the system. This is the definition or work energy theorem. Next is dash of two particle system depends only on the separation between the two particles. The most appropriate choice for the blank space in the above statement is potential energy, because potential energy is a state dependent quantity. So potential energy will depend only on the separation between the two particles. Next is a small block of mass m is kept on a rough inclined plane, inclination theta, fixed in an elevator. The elevator goes up with a uniform velocity v and the block doesn't slide on the wedge. The work done by the force of friction on the block in time t will be, okay, as the block is not sliding with respect to wedge, we can say friction is balancing mg sine theta. So we can look at this diagram. This is the wedge lift is moving upward and it displaces by an amount vt in time t. So for no slipping, friction is mg sine theta, and work done by the friction will be force, which is mg sine theta, into displacement into cos of the angle between them. The angle between displacement and friction is nothing but 90 minus theta. We can take this as theta, so this will be theta and this will be 90 minus theta. So cos of 90 minus theta is sine theta, and here also friction is mg sine theta, so we get mg vt sine square theta is the work done by friction in time t. In the next question, there's a block of mass m which slides down the smooth vertical circular track. During the motion, the block is in, obviously the block is moving in a circular path, so it is changing its direction of motion, so velocity is changing, hence the acceleration is there, hence we cannot have any kind of equilibrium. So option D will be the correct answer. There is no equilibrium, neither horizontal nor vertical, and not also radial. The next is a particle is rotated in a vertical circle by connecting it to a string of length L, keeping the other end of the string fixed. We have to find the minimum speed of the particle when the string is horizontal, for which the particle will complete the circle. We already know that the speed at the bottom, minimum speed at the bottom should be root 5 gl, the minimum speed at the horizontal level should be root 3 gl, and the minimum speed of the particle at the top for complete circular motion should be root gl when it is performing circular motion with the help of string. So root 3gl should be the answer because the string is horizontal in the given question. Okay, enjoy.